Good afternoon, everyone. Apologies for the delay. We've had a few technical difficulties. Welcome to MSCAC Talks. MSCAC Talks is a monthly seminar series that brings together the tech community, so more specifically researchers, industry experts, end users, developers, and so on, to discuss exciting topics at the forefront of technological innovation. I'm excited to introduce our guest speaker for today, Professor Joseph J. Williams. Joseph is an assistant professor in the Department of Computer Science at the University of Toronto. He's also affiliated with the Department of Psychology and Statistical Sciences. In addition, he is a faculty affiliate at the Vector Institute for Artificial Intelligence. Joseph's talk today will focus on enhancing user experience using AI for adaptive A/B testing. With that being said, I'm going to pass it over to Joseph. Thanks, Joseph.
So I'm going to start by actually A/B testing these slides, titles. So enhancing user experience using AI for adaptive A/B testing is one way of formulating this talk. More to elaborate on that, here's an alternative arm. Perpetually enhancing and personalizing technology for learning and health behavior change using randomized micro experiments to integrate psychology, crowdsourcing, and statistical machine learning. And so basically this talk is all about how can you think about using micro A/B experiments to test ideas you have about how to improve people's experiences, how to get people to take action, how to help them learn, how to help them change behavior. And we're going to present a framework, an approach for doing this in a way that brings together different disciplines to solve real-world problems while advancing research across fields from psychology to human-computer interaction to applied machine learning and statistics. And there's a URL here, tiny.cc Williams talk. So you can go to that browser, tiny.cc Williams talk in your browser. And it's actually got the slides from today. And you can add any questions you have in the Google Doc as well. I can see them after. I'm hoping that sound is coming through. Someone please interrupt me if not, because I'm hearing it dipping out a bit. Or in general, if I'm doing anything dumb, like not sharing my slides appropriately, please jump in. And if people are interested, we have a mailing list, tiny.cc join IA extended, that anyone can join at any point in time and drop in on lab meetings, hear what's going on. So especially I'm focusing on people from an industry background. So as you kind of think about this talk, questions you can ask yourself might be, how would I do better A/B testing to improve the benefits to users? Conversions from a website, from a product, increase revenue, or other metrics I care about. What are the user behaviors you want to impact that you wish you could wave a magic wand and we'd improve on them? And in my lab, we're pretty open to consulting and research grants to solve real-world business problems. And you're welcome to throw out ideas. But I'm going to present research we've done so far in domains that are more about social good. For example, education, health behavior change, mental well-being. So the Intelligent Adaptive Interventions group is our group. And I put pictures of the grad students, 7 in computer science, 2 in statistics, and 1 in psychology. And fundamentally, our lab is about experimentation to enhance design in the wild. So our Intelligent Adaptive Interventions lab focuses on how do we perpetually enhance design of in the wild systems using randomized micro A/B experiments. And what do we mean by in the wild? Here's an example. How do we help people learn more by A/B testing which explanations we give them, whether it's on a Wikipedia page or an explanation you give someone in an email? How do you know that that's the best explanation it could be? How do you know there are not better ideas out there for different people? Another example would be there are thousands of apps in the App Store for mental and physical health. But how are these really the best versions they could be? How can we do things like A/B test the questions they ask to help people reflect on emotions? How do we test out which text messages get people to exercise? So if we get a sense of the idea that you can take an interface that's in the wild, people are using it, and then constantly improve its design with micro experiments. So how do we do that? And why do we do that? So I think we're especially excited about the promise of technology to enhance education and health. If you think about it, the whole promise of the internet is that you can go to a massive open online course, an on-campus course, or just Google or use Wikipedia, and you can learn anything you care about. You can get an explanation of how to program better, so you can get a better job, or you can get explanations of how to handle conflict or manage stress better. If we could really achieve this potential, we can help every one of 8 billion people to be more effective personally and professionally. However, you can all think of examples where you find a resource and it's not really helping you learn. Some explains things in a way that doesn't really move you forward, or you forget it. So what we need to do is to figure out, how do we experiment and test out which explanations, which actions help people learn. Another example is mental and physical health. Every human being is going to have times when they're anxious or they're sad, and it's going to impair their happiness as well as their capacity to help other people. Physical health, things like exercise, have a huge impact on people's longevity, dealing with things like diabetes, as well as their happiness every day. And there are interventions like digital cognitive behavior therapy that are so effective that in the United Kingdom, doctors can write a prescription for online CBT. But again, often these things aren't engaging. People don't stick with them. And this is such a massive problem that you can't just provide a solution. You have to constantly improve and enhance it. A key focus of our lab is we try to think of helping the entire student. So how do you think about improving formal education in courses, as well as informal learning of skills that promote mental and physical health? And I remind everyone that all 11 billion people in the world are lifelong students. We're all constantly informally learning every day. We ask friends for advice on how to manage stress. We try to learn how to interact with specific people, and we try to learn how to solve problems we face every day. How can we use technology to constantly enhance and improve that? And really broaden our idea of all the ways we can help people learn, by which I mean acquire a piece of information that might change your behavior. You're learning when you receive an email from someone. You're learning when you talk to the person next door to you. What would it look like to think about A/B testing in all those scenarios, instead of just assuming we know, trying to test it out? So just in the past 3 years, we've designed and deployed over 50 randomized micro-AV field experiments, from a large first-year computer science classroom with over 2,000 students to text and voice services for mental well-being that anyone can sign up for. I'm going to start this talk off by just giving examples of what they look like, so you can imagine the applications you might care about, and I'll transition to the main framework for how we do A/B testing and examples of that. And especially ask yourself, how can you map these examples onto the interfaces you care about, the behaviors you want to influence? One line of work by Angela Zavlet and others is investigating the impact of online homework reminders using A/B comparisons. For example, asking students, testing out different ways of asking them if they've set a reminder to do homework. How could they do it earlier than last week? So we explored a range of different ways of framing the emails, using different psychological theories to try and get them to impact the behavior. And one thing we find here is a lot of the things that people are very sure are going to work have no effect. So it's important to test your assumptions about whether emails you're sending every day are actually achieving their goals. And you can imagine many settings in a business real-world setting, emails to get people to engage with the product, emails to get people to connect. How could you A/B test those better? Another example of a set of studies by Ilya Musabarov and Panchan and others concern prompting people to reflect when they're trying to solve a problem. For example, intro programming. Where are you stuck? What alternative approaches you can take? That's one arm A. What are the other messages you could ask someone to help them reflect while they're solving problems? And you can imagine any setting where people are trying to learn how to do something or just achieve a task. How do you A/B test which questions you ask them to help them think things through? In the context of stress, we've got interventions we've deployed with thousands of people that help people reimagine that being stressed can actually help you do better. It doesn't just distract you or make you do worse. And we've shown that this can actually increase people's scores on the test. Another example might be prompting people to set goals. So relying on theories like mental contrast and implementation tensions, how do you prompt people to set goals, whether it's for a day or a week, so people can use their time better? A fundamental problem we all face. In terms of mental well-being, we've also built web and text messaging-based programs that have been delivered at scale. An example here might be where people can sign up over 4 weeks, 8 weeks to receive every day sequences of messages that give them advice and help them reflect, based on principles like cognitive behavior therapy. And that's an example of one paper that looked at how we can improve these. Another line of work is using chatbots to help people reflect and change behavior. So in this setting, we use GPT-3 and we do micro experiments on how we initialize GPT-3 to have different personas and different approaches. And this allows people to talk through a stressful situation they're going through. And as you can imagine, everything you do with a website, with a person, with an email, you could imagine as conversation. So it's a very powerful medium through which you micro experiments to understand how we can make these interfaces better and more effective for people. And it's surprising how often people don't do A/B testing. You build a model, you think really hard, you're a smart person, and you deploy it, but you don't deploy the system so you can keep testing components of itself, keep testing what questions it asks, what messages it gives, so it keeps getting better and better over time. Every single piece of this conversation could be A/B tested, and it's surprising how rare that is. So why would you want to use microexperimentation for design in the wild? We think of this as actually not the only method you should be using, but we're trying to push the frontiers of how people do this effectively. We find that if you get decisive data from a microexperiment, it's one of the strongest tests of an idea. A lot of things that you would swear would work, you deploy it and you find out it doesn't actually do it better than anything else. Even when you don't get conclusive results, this is very valuable because it requires you to be precise in measuring. How do you quantitatively specify what behavior you want to change? What exactly how are you gonna measure what you're trying to get people to do? And also precisely specify alternatives. Instead of vague things like a friendly chatbot, you have to actually turn that into specific examples of what you mean by that and how it relates to people. And a big value here is that using this large-scale data from experiments allow for rapidly improving and changing things on a much faster timescale of days or weeks versus years. And a key theme we take is to experiment with experimentation. How do we take a broader view of what it means to run a randomized experiment? So it's not just accepting and rejecting some predetermined and well-defined hypothesis for the statistical test. Think of it more as a thinking tool for exploring what's the complex design space, for example, of generating and improving instructional content like explanations. And we'll also talk today about thinking about applying AI to randomized experiments to see it as an engine for constantly improving systems. The vision we have here is that you want to perpetually improve interfaces after they're deployed. For example, like a real teacher does. If you think of online homework or any website versus a real human being, an in-person teacher, in online work, instruction rate changes. You might get the same answer explanation to hundreds of people. And it's not using data gathered over time, and it's not also using new ideas. Whereas a real teacher varies interaction. Every time you explain something to someone else, you might change slightly what you say. And when you test these different explanations, A versus B, over time you can learn actually what's better on average. And you can also learn what might work better for some people, such as when is a simple explanation better for someone with low knowledge or a more complex one better for someone who's got some background. So how do we basically create systems that are much more like real teachers and real humans using microexperimentation? I'll demonstrate this with an example of a story. If you think of trying to combine a human-computer interaction approach to education, instead of an instructor simply thinking hard about what they're going to do and then choosing one of the best options, how can you make it easy for them to deploy different options? For example, explanation A, B, or C. And this is where we also rely on systems that allow instructors to collaborate with cognitive scientists and psychologists who've done decades of research on how people learn and make decisions. But this collective experimentation shouldn't just stop from 2 or 3 conditions. It should continually improve. So you don't just deploy an experiment once in a course from a semester. It's constantly running for the next 10, 20 years and getting better and better over time. It also needs to be dynamic, where as data is coming in, you keep analyzing and getting more and more sure about what's effective, what's not. So you can remove things that don't seem promising and add in new ideas if you see that things could be better. This could lead in the long run to enhancements as well as to personalization, where you give things with higher probability that are effective, or you give things with higher probability to certain subgroups of people. And that's where we incorporate Bayesian statistics and machine learning. So if you get a sense of this vision of experimentation to allow collective experiments, dynamic experiments, and personalizing experiments. We've actually built a software infrastructure, which we call the MOOC infrastructure, because it's developed in MOOCs, but honestly, anyone can plug it in. It's based on actually extending the kind of infrastructures in companies like Meta and Microsoft and adding additional capacity that they don't necessarily focus on because we're bringing a scientific perspective to it, especially in allowing people to test many ideas at once. And so anyone can use this framework to achieve this vision for collective dynamic personalizing experiments. And so this actually is the basis of a recent $3 million NSF grant over the next 5 years across 4 universities, where we're basically make it possible for anyone to actually run these kind of collective dynamic experiments in any real-world interface. And that's based on this MOOC framework. It's also the basis for us being top 3 finalists in a $1 million challenge for what's the future of educational experimentation infrastructure from the US Department of Education. So that was a long run-up, but that was probably the most important part to understand, which is we have this vision. How do you take any real-world interface, any website, any email, any text message, any app, and turn that into a perpetually improving system that gets smarter and better over time, that helps you figure out what does and doesn't work? And the approach there is to reimagine experimentation to be collective, dynamic, and personalizing. So I'm going to talk about one study that illustrates this approach, where we crowdsourced and dynamically tested explanations from learners. And what we show here is that by crowdsourcing explanations from learners and then testing them out with a micro experiment that dynamically and adaptively changes over time with machine learning, you can actually end up with explanations that are as good as those of a real instructor. A second example of this is thinking about dynamic experiments where you can give people tools, such as instructors, for running adaptive experiments in everyday life, and how this actually helps them go beyond what they might typically do and see how this tool of experimentation can actually be an engine for real-world improvement. We also highlight the problems that arise here from a scientific perspective, where there's a urgent need to develop algorithms and statistical tests that are more reliable than the status quo for doing these adaptive experiments, so people can have confidence in the conclusions they're drawing. And I finally close an example of how we can use experiments to discover how to personalize, and in particular, what we're aiming for in this setting. What I would say, though, is that this entire vision is something that will take place in the next 50 years, 100 years, and a key challenge is understanding how best to do this in different contexts. And so I can point to a bunch of different ongoing work later, but thinking especially about what does interpretable interactive machine learning look like when you build intelligent systems that are driven by experimentation, by adaptive experiments? How can you ensure that instructors and scientists can interpret data from these experiments and understand why it's giving particular suggestions to a person? And also, how do they interact with it? How do you make it smarter than just the algorithm running on its own? So starting this first line of work, a system that crowdsources and dynamically tests explanations from learners. So we call this AXIS, the Adaptive Explanation Improvement System. So here's the problem we try to tackle here. If you look at online courses, often they give problems to students, but all students get is an answer on whether it's right or wrong. And there's good psychological research showing that if you give people high quality explanations, such as those that identify a principle, this can have a big impact on them learning and also generalizing what they've learned in the future. But if you go to instructors, they're going to tell you, Joseph, I have 0 explanations right now. How am I going to have the energy and time to generate multiple explanations to then be A/B testing them? So how can we tackle this? Well, in past work, I've looked at how when you prompt people to explain, for example, explain why an answer is correct, this can actually help them learn more than if they're even given an explanation. So how do we actually prompt people to explain as an activity that helps them learn, but then take that explanation and use it for A/B testing? So the idea here is that prompting someone to reflect and explain to themselves can help them learn, but as a byproduct, it's also an entry into crowdsourcing. You can then actually gather these explanations and keep adding conditions or arms to be tested. Of course, that raises other problems, right? How do you know which of these is good? So what's the approach? Well, here's where we want to do dynamic or adaptive experiments. So I use the word dynamic and adaptive interchangeably. In an adaptive experiment, you'd actually analyze data in real time and try and eliminate explanations that don't seem to be helpful and keep those that are. And that would be a quality control over what people are generating. Does that make sense to everyone? So here's an example of what users actually went through. They might be doing an online homework problem. They'd attempt it. And eventually they get told the correct answer. We then prompt them, give them an explanation of why the answer is correct. And that's what we're A/B testing. This is the MOOClet, the Adaptive Intelligent Interface. You've got like an intelligent explanation machine in here. And we ask them to rate how helpful was this information for your learning. And we chose this actually very carefully because this doesn't actually measure whether they're learning from this. We found that by framing it about how helpful it was for their learning, we actually got a good metric that was more predictive sometimes of what would help them learn in the long term than whether they got the next problem right. And then we tell them to help you learn, explain your own words why the answer is correct. And as I mentioned before, this can help them, but you all see why it's a bit sneaky. Sneaky in a good way, right? Because if the explanation was longer than 50 characters and they checked off saying that it could be useful to other people, we add it to our pool. So do you all see how this is now an engine for crowdsourcing from learners in a way that benefits them as well as the system? So now the question we have is, how do we identify which are better, worse explanations? And how do we rapidly use that data? So in this dynamic experiment, this is the fundamental problem in a dynamic experiment and also in reinforcement learning. And the most simple version we will look at, the most fundamental form, is what's called a multi-unbounded problem. And the idea is that we're going to use an algorithm that you can think of as randomized property matching called Thompson sampling. And the key idea is this behind Thompson sampling. Your problem is you have a set of actions, explanation A, B, C. You have a reward or a metric you want to optimize for. You want to give people explanations that they rate as helpful for their learning. Now, you have to test out explanations to get data. And how do you know when you've got enough data to give something more often? That's the problem you're trying to solve. And so the approach of the policy or policy learning algorithm, Thompson sampling, is basically to assign an explanation with a probability that is proportional to the probability that this is the highest rated explanation. So for example, if after 50 participants, people are rating explanation 1 on average a 3 out of 10, and explanation 2 on average a 7 out of 10, explanation 3 on average a 4 out of 10, you might then see explanation 1 being assigned 15% of the time versus 65% versus 20%. And those numbers correspond to the probability, according to your model and the data so far, that that's the highest rated explanation, or that's the best explanation. And just to provide some technical details, people can fade out if they don't want to follow, and I'll bring you back in. We actually use a very simple model here that's widely applied, and there are lots of ways to improve it, but it was pretty effective in this scenario. Basically, the idea is this. We're taking a Bayesian approach where we model the probability of an explanation being rated helpful as following a beta distribution with parameters alpha and beta. And we set alpha as 19 and beta as 1. And what that means is before you see any data, you act as if you've seen, for each explanation, 1 9 out of 10 rating, 1 10 out of 10. So you're optimistic, but you don't have much data. So you can be easily overwhelmed. So that's basically your prior distribution. The probability of an explanation being rated helpful follows a beta distribution, where you think it's good, but you don't have strong beliefs. Now, how do you use data as it's coming in? Well, here's where you assume that the rating, the reward, follows a binomial distribution with 10 samples, and the probability of an explanation being rated as helpful is drawn from this beta distribution. So with this beta binomial distribution, using these conjugate priors, it's pretty efficient to update and it's interpretable to people. You can think about this very intuitively. Every time someone gives a rating like 7 out of 10, it's that they give 7 thumbs up and 3 thumbs down for explanation A. If explanation B gets rated a 9 out of 10, it's like 9 thumbs up and 1 thumbs down. And so you can use Bayesian inference to constantly update the beta distribution, which gives you an estimate of what the actual probability is an explanation will be rated helpful and how confident you are in that probability. Does that make sense intuitively to people? It's basically the underlying beta binomial model for the probability of an explanation being rated helpful, which you then use to assign people with that probability. So as you get more and more evidence it's helpful, you assign more often. Okay, so picking back people up. When we deployed this, we aimed to deploy this actually in a very data efficient setting, where we just had 150 people, the size of a university class or a couple K-12 classes. We want methods that will work even with sparse data, which is a very different kind of machine learning challenge. How do you most efficiently use data to help in these real world applications? So at first, there are no explanations. People are just explaining to themselves why the answer was helpful. Eventually, someone generates an explanation that gets added to the pool. Then there might be two explanations. And as people are rating them, you might see that explanation 2 is being rated higher than explanation 1. So there's an 8% chance they're being presented. So over time, you keep adding explanations and you adjust it to give higher rate explanations more frequently. So at the end, what you get from this Access Adaptive Explanation Improvement System is a probability distribution over explanations. So for example, in this one, you might have one explanation being assigned 80% of the time, and the 11th explanation just 2% of the time. Is it clear how now higher rate explanations are given more frequently? So what this shows is that you are going to get pretty quickly a way of assigning more highly rated explanations more often and phasing out lower ones. But you might ask yourself, well, is there evidence this will actually lead to learning, that we're getting explanations that help learning, not just a metric optimizing for? And so we did a separate randomized study where we compared the original problems, just what people had with no explanations, to problems that had the Access explanations. So these explanations drawn with the same probability Access was giving them for the 150th participant. And this allows us to figure out if we compare Access to no problems and we give people a test before and after, how much do they learn? But we have some alternative hypotheses we want to rule out. Maybe actually it's any explanation. The Access adaptive experiment isn't really helping much. So we include explanations that were filtered out. These are explanations that Access gave very low probability to test the idea that maybe it's any explanation could be useful. And as a gold standard, we finally gave an Instructor explanation that they are sat down and wrote carefully if they'd had time. So what you can see on the vertical axis is accuracy increased over time. So original problems with no explanations compared to Access aren't as effective for learning. Because what you see is a 12% increase from like a pretest where you give people problems to solve and you see how well they do. Then they get the Access explanations and you give them a test afterwards. So there's an increase in how the accuracy in solving your problems based on the Access explanations. So that's actually compelling because these were generated by learners as a byproduct. But once they go through this adaptive experimentation algorithm, you're getting explanations that aren't just higher rated, but help learning. And of course, you could be a doubter, right? Maybe any explanation would have helped. But the filtered out explanations, the ones that have lower probability from the adaptive experimentation algorithm, those are like getting nothing at all. They don't benefit. And now, how good would this have to be compared to an instructor to be useful? Would it be 50% as good, 30% as good? Because it's an automated system that involves learners. At least in this setting, it's surprising, but there actually isn't a significant difference between generating these explanations and adaptively selecting them and a gold standard explanation written by the instructor. And so it's an interesting question in what context it's going to be much worse and when it's still worth doing, and in what context it might even be better because learners might understand other issues other learners struggle with. In fact, the instructors even reported that they look quite comparable to their own, even though they had a personal preference for theirs. So what are the contributions of this work? This is a scalable method for collective experimentation. Crowdsourcing explanations is a byproduct of learning, which you can think of as learner sourcing, idea we've coined with other people. It's also illustrating an example of using dynamic experimentation to rapidly use data to sort more and less promising ideas. So I'm going to move on to the second set of work, which is thinking about dynamic experiments. What does it look like to give people tools to conduct these dynamic experiments? And what issues does it raise that we need to tackle to have scientific trust in the results we're getting? So if you think about it, traditional experiments are arguably just a special case of dynamic experiments, right? It's like you do 50-50 for 200 users, and then a new experiment with 50-50 for X users, or 0-100 for 10,000 users. The idea is that often we're just like running an experiment and then we just stop, and you have to make a hard decision. But that's actually the kind of adaptive experiment. It's just one where you only adapt once and then you're done. You go from 50-50 to 0-100. How do we actually do better in terms of adaptive experiments that will constantly learn and improve over time? So there are two questions we tackle in that setting. A is how to make experimentation more useful for instructors or any designer of a website. And then B is how do we help researchers analyze and use data from these dynamic field experiments? And here's where we have the trade-off helping users and being certain about scientific conclusions. And you're going to lose something because adaptive experiments essentially stopping experiments. But the holy grail to reach here would be how do we accelerate scientific discoveries and use data to more rapidly help users? So this work on what we call Instructor-Centered Experimentation is published in a CHI paper, which you can read more about there. And the kind of key idea here was to build a system where instructors could deploy experiments and obtain data with minimal programming. So if for people in companies, this would be an end user tool for helping someone in your company to run A/B tests, even if they're not a software engineer or data scientist. And again, second goal is more rapidly use data for practical improvement. And that's an example of the interface we built, where people could just add versions and remove them by just editing without having to worry about deployment. And this is an example of a dashboard they would see, where, for example, while an experiment's running, we would want to support interpretability. For example, them being able to see right now at this moment in time, there's 23% of getting the quantitative explanation 1, or 77% of the analogical explanation 2. So instructors can actually monitor what's happening. And in particular, they can see how this is based on the data. The mean student rating, 1 to 10 of explanations, and the number of students. And again, the dynamic experimentation approach, just repeating what I said before, is the idea that probably the students assigned to a message is proportionally probably that message being highest rated. So you go from 50-50, 60-40, 70-30, improving over time. So we deployed this with 3 Harvard instructors who were able to use this to deploy in their course. And here was some of the qualitative insights from them. It really lowered the barriers. Like, they weren't aware of any tools that do this kind of thing in their teaching. And many of you can think, how often do we do that in our own teaching? Take our different ideas and test them. And they really liked that it helped them reflect on pedagogy. One said, I never really seriously considered testing multiple versions we're doing now. Even if we don't get any significant data, that will have been a benefit in my mind. They also liked that it made research practical. And this is again the collective experimentation idea. This is a viable tool because it's putting in the hands of the teacher to understand how their students learn, not just in broad terms, but specifically in their course. You must know plenty of general things as a researcher about how students learn, whereas I know specific things about how they get calculus. So how do we design tools that allow us to bring together those different ideas in the explanations and interventions we create, and then dynamically adapt them? And that was a key feature. Dynamic adaptation could directly help students. So instructor said, this improved the experiences of many of the students by giving them answers that are more helpful. The earlier ones can help improve the experience of the later students. So that's pretty neat. And we have some data. I think this is a great area for future research about what students think of this approach. But at least some students who provided certain data, one of them said, I assume companies are always A/B testing on me. At least the data I provide can help other people learn. Now, this is promising because what we introduced in our paper is really a whole different paradigm for a field like education. I think experimentation, not just as a tool that scientists use, but actually something practical they can use in their work. They can help them reflect on different ways of designing experiences. But now, how do researchers use dynamic experiments? For example, when you adapt experiments in different settings, how much is statistical power reduced? And as a refresher, statistical power means that when you do a test, to see if there's a difference, it's the probability of correctly detecting the effect when it exists. What about false positive rate or type 1 error? This means that if there's no effect, no difference between 2 explanations or arms, then you falsely think there is one. So this paper has a lot more details on that in Journal of Education Data Mining. But one finding here is that you are going to lose in certain settings, like when you have 2 arms or conditions, You're going to lose power because you're putting many people in one condition. You're essentially stopping the experiment early. And another issue is that we've been characterizing in the last couple of years, different kinds of biases that show up. So there's work on theoretical level suggesting that you might get bias estimates of means, but what we've been doing is showing in these particular settings exactly the nature of those biases. For example, you get an increased false positive rate because when there is no difference in arms to the same rating, because of a random low, where something looks worse by chance, what happens? Well, if it looks worse by chance, the algorithm that's adaptive will stop sampling from it and put people in the other arm. And so what happens there is that at the exact moment when something looks worse by chance, you stop sampling, and so you get a biased estimate of its effect. And so you might get more and more confident in one arm being better and be super sure that it's at a particular level, but you never actually go back and get more data from the other arm. And so the false positive rate can go up to 13% compared to 5%. And what this means is that all those companies that are doing these adaptive approaches, that are doing them now, there may be issues in how they're analyzing the data that they have to revisit. On the other hand, some companies and practitioners say, well, I can't do any adaptive experiment. I should do nothing at all. I think that's also a problematic approach because they're not recognizing the fact that even if you lose false positive rate to a certain extent, and there's some issue with those conclusions, there's still a big benefit, which is using data to help people. And the proper question is doing an adaptive experiment worse than just running an experiment, testing it, and then just making up a decision based on how the data looks from one sample? I think that's an open question, and it's probably the case that there are better ways to do this. And the question is not, should I do adaptive experiments or not, but what kind of adaptive experiments should I be doing? Does that make sense? And so on that note, one line of work we're doing now, and I can talk more later, but I just want to dip people's toes into it, is developing algorithms and statistical tests for these dynamic experiments. So one work that we submitted is an algorithm that better trades off helping participants with statistical analysis. So we call this almost like statistically considerate algorithms for experimentation. And the key intuition here is that instead of just doing a traditional experiment, 50-50 the whole time, or an adaptive, where you adapt it with the property of assignment, what if we actually do a hybrid approach where X% of the time, we're going to do 50-50 assignment, and then 100 minus X% of the time, we're going to do adaptive assignment using Thompson sampling. And the key idea here is that instead of that X% being 0, which is full adaptive, or it being fixed, like 10% or 20%, we developed a new algorithm which we call Thompson sampling posterior difference. And the key idea here is that it adapts the probability of doing a traditional 50-50 assignment. And the probability of doing traditional 50-50 is, what's the probability? The difference between two conditions is small. So what's the probability? It's small. And the practitioner, the scientist, or the instructor or designer decides what small is. For some people, small is 2%. For some people, it's 8%. But I think this is a very powerful approach. That's just one instance of a class of approaches, because what it says is this. When a difference is small, then it is a high probability a difference is small. Then do lots of traditional experimentation. Assign 50-50 because you're not going to lose much. There's not much benefit to be gained because it's a small difference. So do lots of traditional experimentation. When the difference is large, do much less traditional experimentation because you want to actually use that data to help more quickly. And that's in fact what we find when we contrast this against other approaches that are state of the art for doing this kind of adaptive experimentation. Does that make sense to people? So one of many classes of algorithms that can trade off traditional experiments with adaptive experiments by actually trying to quantify what's the probability that there are small differences or not, which can then actually balance the best of both worlds. Another line of work, especially relevant to people on the statistical side, is what do statistical tests look like for adaptive experiments? And we've looked at a number of different approaches here, but the one that's been most promising is actually a novel hypothesis test that Fred Houchin-Song and others working on, which is called an allocation property test, where instead of just comparing sample means using the traditional like t-test or z-test, what we're actually doing is coming up with a new test statistic that actually looks at how often the probability of assignment changes away from 50. What's the proportion of times you get an imbalanced probability of assignment? And how do you actually quantify under the null hypothesis of no difference, how often that would occur? So by designing this test to be sensitive to how often the assignment properties get big, and comparing that to what you'd expect under the null of no difference, versus when there is a difference, this is actually a much more sensitive test. It's got actually lets you control false positive rate right back down to 5% or whatever you set it at, and actually increases your statistical power. And this is a really nice example where we design a statistical test. We design the statistical test to incorporate properties of the algorithm. And so I think this is an example where you need to combine statistics and machine learning to be very clever about understanding how the algorithms work, while also understanding the way hypothesis test works. You can actually get the best of both worlds and again, beat the state of the art. And allow people to draw valid inferences while helping people more quickly. So just to summarize, in terms of dynamic experiments, I gave one example of making experimentation more useful for instructors, and also tried to help researchers analyze and use data from dynamic field experiments, which is again coming up in a real world setting. What are algorithms that are better for analyzing this kind of data? And what are statistical tests that are better suited to the way that these algorithms behave compared to traditional experiments? I think this is especially important because dynamic experiments are a very powerful way to bridge human and artificial intelligence. If you think about it, any interface component, you can embed a micro experiment into it using a Mooklet framework, and you can turn any interface component into a perpetually improving intelligent agent. From the emails that you're being sent to someone to your website or your homepage right now, embed a component that's constantly testing out ideas and running these algorithms to detect what's working under what context. So it's basically a way of thinking, how do we embed machine learning AI into any real-world interface? And now you have to ask yourself, well, how do we do that in a way that combines human and artificial intelligence? And micro experiments are very well suited to this. Human beings can contribute to actions, and they can specify what metrics to optimize. So they can generate different ideas on how you should optimize, how you should select what's the best. The algorithms are effective because they analyze data and make updates in real time. And they specify very clearly how they're updating data. It's not just someone looking at data and making a decision. The algorithm instantiates those rules. And so this is a range of interesting directions for interpretable ML or AI. How can human beings understand the way the algorithms are behaving? How can human beings understand what the data is suggesting? And also interactive ML and AI. If, for example, you optimize an algorithm like is being done right now to all of us for Instagram, Facebook, Reddit posts that people like, this can actually end up spreading misinformation or even addictive kind of content. This is where human being needs to step in and look at the data and interact with the algorithm and say, don't just weight engagement. Weight people's ratings of quality by particular experts, or include a loop that makes an API call out. I see this content is very popular. How do I make an API call out to some set of experts who will then monitor and evaluate it? And then that could allow them to interact with the algorithm so that it brings it back on the track. So we can avoid these really problematic issues of misinformation where algorithms run wild and get the benefits of combining human and algorithmic intelligence to help people more effectively. So hopefully you've seen some interesting ideas about how to instantiate this. I'm just going to close with another key direction for the future that's quite challenging. And this is helping people discover how to personalize. So here's one very simple example with emails, something we all do every day. In this setting, we sent an email to people where we asked them about why they had not been participating in a course recently. You can imagine what you would want to test in the email. And we compared a brief message, would you please take this short survey to improve the course, against one that mentioned the absence. It's been a while since you logged in, so we're eager to learn about the experience. Would you please take this short survey? And so now, thinking about how to optimize the personalization, if you look at the response rate on the vertical axis to the briefest mentioned absence, if you just look overall, you'll be tempted to think, well, actually, there's no effect. It doesn't really matter which email I send. People respond at the same amount. But you all see why that's a problem. Actually, if you parse the data by low activity versus high activity, so low activity were people who had never really logged into the course or done much, whereas high activity were people who used to log in regularly but had recently dropped off. And what you can see here is that there's some evidence that brief messages work well for people who are always low activity, potentially because they're more likely to read something brief. But people who are high activity more likely to respond to the mention absence message, maybe because they're trying to explain why they were recently not active. And why is this so important? Well, if you actually were to try to optimize by not just doing what's best on average, but actually saying, if you're low activity, then I'm going to give you the brief message more often, 80%, 90% of the time. If you're high activity, I'm going to give you the mention absence message. You could actually increase your response rate by up to 14%. So why is this so powerful? Well, it shows us how actually we can optimize people's responses without actually changing our actions. We've got the same amount of actions. It's about being clever about discovering what works for who. It's also allowing us to advance science in the sense of test hypotheses about what's working for who in different contexts, as opposed to assuming we should do the same thing for everyone. I would also emphasize that everyone talks about personalization. We all believe we're special and we're snowflakes, and we are. But empirically, I would challenge everyone here to show me an experiment where A is better for one group of people and B is better for another. A lot of our intuitions just break down. Experiments are viable because they show you that you're sure that I'm different from this person along this dimension, but when you have to put the rubber to the road and actually test it out, it's very hard. You have to really think carefully, and a lot of our intuitions just don't pan out. I want to also emphasize this in a very important way, which is there are a lot of interesting statistical questions here. For example, imagine that actually people, let's swap these labels out, right? Let's imagine, for example, that there's a statistical minority, and what's best for the statistical minority is different from what's best for the majority. So for example, imagine that actually the brief message is better than the mention absence. But let's actually imagine that low activity people are 90% of the population, and high activity people are just 10%. Well, what's going to happen is that on average, what looks better is going to be what's best for people who are greater numerically. And can you all think of a time when that's a problem? If, for example, you're teaching a course and you do something because you think it works for most people, and it may, you may actually be systematically disadvantaging people who are in a statistical minority. And if you think about it, that's a big problem, especially in STEM courses. Who are statistical minorities? How can we support diversity and equity if we're not having methods that are allowing us to figure out that people who may be a statistical minority, whether they might be women in STEM or particular groups, or people who might be first-generation students, that what's most effective for them is not actually what looks to be best on average. Does that make sense to people? Do they see why doing a data experiments we can keep exploring over time and collect data at a large scale is really key for figuring out if what you think is best may actually be different for some subgroup of people, especially if they're a statistical minority, especially if they're underrepresented. And this is a big focus we have now, which is trying to think of how we use experiments to discover how to personalize, how do we think about them differently, and how do we use qualitative methods so we can guide which experiment design, like what variables we're going to personalize on, and how do we design these algorithms to better balance personalization versus enhancement. For example, looking at different contextual bound algorithms, most of the current approaches aren't quite what we want to use, and we have a couple of papers looking at them. So I guess let me review and summarize everything I covered. I started with this vision of perpetually improving systems. How do we take any interface, from an email to an explanation to a text, and turn this into an intelligent, perpetually improving system? And I give you all many examples of what we've looked at in experiments. And I invite you all to think about, as you walk out this room, as you pursue everyday life, what are the components you wish you could make into an intelligent, self-improving system to help people? We outline the approach to this is reimagining experiments to be collective, where multiple people are involved in generating conditions, to be dynamic, where you use machine learning and statistics, analyze it over time to give what's better to people, as well as to get greater confidence in what's effective or not. And personalizing. How do we discover what's best for different people, or what's best for the same person in different situations? And so I gave one example of this, the Access Adaptive Explanation Improvement System. And why was that important? Because it showed us how you could actually crowdsource from learners explanations by asking them to reflect, and then use these to give to other learners And once we would actually dynamically test these out with these adaptive experimentation algorithms like Thompson sampling, we identified explanations that help learners just as much as those from a real instructor. And then consider how dynamic experiments can be embedded into tools for instructors and other practitioners to turn experiments from a scientific tool to something that actually helps them improve their everyday products and makes them reflect more on alternatives they could engage in and how they might evaluate these. But also flagged the kind of work that is needed and that we're doing now for coming up with algorithms for adaptive experimentation that balance helping people with reliable scientific data, such as combining traditional experiments and adaptive experiments with the approach I mentioned, like Thompson sampling plus zero difference. And also the work we're doing to develop new statistical tests that are sensitive to the machine learning algorithm's particular dynamics. I gave an example of discovering how to personalize and how we can use experimentation to optimize what's best for different subgroups of people after we discover that, and why that's so important, especially for improving diversity, equity, and inclusion for people who may be statistical minorities, rather than assuming that we know what's going to be best. And again, this is all just a first step to an approach that I think people are taking more and more of the next 50, 100 years to try to actually reimagine how we can combine human AI to constantly improve a railroad interface using my experimentation as a bridge.
Excellent. Thank you, Joseph, for an insightful talk. We will now move on to question and answer. And apologies for the online audience. I know you can see Joseph's slides, you can hear him, but unfortunately you cannot see him. I assure you that he is here. So we can move on to questions now. I want to open the floor to our in-person audience. So if you have a question, please raise your hand, tell us who you are, and then proceed with your question. Okay, so no questions in person. Joseph, we can move on to the question online.
Stop screen sharing. Great, so one question online by Roichi Juan was, while most of the work has been done on students and users in need of mental health support, given that user experience for older adults are also important but often ignored, would you think there can be possibilities to apply A/B testing methods in older adults? If so, could you provide a few insights on how to translate the A/B testing algorithm to people who might be from the older population? And other people, feel free to write questions in too if you have. So I think it's a nice example of questions focused on how do we apply this kind of approach in different settings, and what can we keep that's in common with what we're doing versus what do we have to adapt, right? So I think that I'm trying to give a very concrete example of how to help people who might be an elder adult, right? Let's say, for example, you're trying to, like our text messaging program sends text messages to people to help them deal with mental well-being on an everyday basis. It gives them messages that ask them to reflect on what they're going to do today to be active, what's on their mind, what are they feeling good about. So how could we actually make that kind of intelligent system adapt to people who might be older adults? For example, if we use that MOOC-led infrastructure, what we could do is we could actually do collective experimentation, where we could ask people who've worked with elder adults, whether it's caregivers or people you can find online, to suggest messages that they think could be especially important. And the advantage then is that the exact same system we've been using with young adults, we can now start to bring in additional messages that we can test out with the older population. We could also imagine that as an elder population gets these messages, you could ask them, is there a message you wish you'd gotten instead? Or what's the problem with the current message you've got now? And I think this is a great example of how, because you've got a micro-experimentation setup, the action space has been broken up into all these pieces. What's that first message you got today? What's the follow-up message? And I think that actually makes it easier to enable collective experimentation by people from different areas anywhere in the world, whether it's someone who's worked with older adults, whether it's someone who's never seen the service before and has some time, or whether it's someone using the service. And you can actually get them all to suggest ideas on the same playing field of what's the message you should get? What metrics should you use to evaluate it? And so does that make clear how, if you want to apply this to another population, you can use the same experimentation approach and find ways to allow people to quickly and efficiently give suggestions about what a better message is to get, or what are the current messages, what are the metrics one should keep in mind. Yeah? Yeah, I'll do this.
Hi, thank you. I'm Lei from Stats. So to me, I feel you were talking about the personalized this A/B testing, essentially covariate adjustment. So using your class as an example, you give A and B version. Well, depending on the person who responds, whether it's a female or male, maybe a native English speaker versus not, they may choose A and B completely in opposite direction. If you lump them together, you may have, get a no effect between A and B, right? So I guess that's what you were getting at. Avoid the confounding. But then in the meantime, I can see in practice, you're going to have to collect that information. That complicates the whole process, no? And then people may not be willing to give out such information. So can you comment on the challenges?
And maybe just want to define people. When you say covariate adjustment, what do you mean by that? Just define people.
Whether the preference for A and B, depending on, let's say, your sex or being native English speaker or not. Just give an example.
Yes. Yes, so I think covariate adjustment is you're not just looking at the effect of A versus B on average, but you're adjusting what that effect might be for different covariates or other variables about people. Like, for example, age, gender, and other things. Yes, so I think I would echo the question back as basically, there's so many challenges that come up when you try to actually have that data, those covariates or contextual variables, and be able to analyze if the effect of A or B or C for hundreds of microexperiments depends on those, right? And for example, some people may not even provide that data, right? Or that data may become available later, right? Yeah, I think those are great examples of challenges that we should be thinking about, right? And I think that one powerful thing about the infrastructure we built, this MOOC-led architecture, and why it's kind of the basis for that NSF grant and the kind of competition on future of education experimentation, is that I think it future-proofs experimentation. What do I mean by that? You can start running a data experiment where you're just looking at the effect of A against B. But because the way the system's set up, if you get data, for example, people start providing their grades later on, like a month or two later, then you've got a system that now you can analyze that data and then go back and adjust the adaptive experiment. By which I mean, if 200 people came in and you didn't have age or gender for them, but then it became available, in most traditional experiments, well, you analyze and you're like, well, I learned something, but I can't change it. But because we deploy this in the wild, in systems, what you would then do is make API calls, would then actually adjust the algorithm you're using so that for future people, person 201 to person 600, we could then actually start to personalize for them. So the idea is if that's one use case where data is not available at first, but it comes in later. And what we did was very carefully build an infrastructure that makes it easy to adjust based on its variables, even if you don't know what they are in advance. Other kind of approaches you could take might also be trying to do some kind of semi-structured learning where you might think, well, are there some latent variables or groups that I'm just not aware of? So those, again, techniques you would apply. So I think these are all examples where we're kind of formulating the problem and how one can tackle it. And they're opening up a bunch of really interesting questions. That's when we assess like a framework, right? This framework of adaptive experimentation is not by whether it's right or wrong, but whether it's fruitful in generating different questions people can ask and how they can apply new techniques or existing techniques to solving these problems like personalization through experimentation.
Excellent, thank you. And I believe that is the end of all the questions. Is anyone going twice? Any questions from our in-person audience? No. Fantastic. Well, thank you everyone online as well as in person for attending. This is obviously the final MSCAC talk for 2022. We look forward to welcoming you again for MSCAC Talks 2023. The next one will take place, in fact, on January 30th with Vera Liao, who is a principal researcher at Microsoft Research. Thanks again, Joseph, for your talk. Thank you everyone for attending. I wish you all a good evening and happy holidays. Thank you.